so like I say, I'm going to kind of plow through this. If at any point I'm going too quick, stop me. All right? So forces. Remember, a force is a measure of how hard you are pushing or pulling an object. It doesn't measure how fast the object is moving. It just measures how hard you are pushing it. Okay? You can measure force with a spring scale, right? And the harder you pull, the more force you're exerting. Or the harder you push, the more force you're exerting. Did everybody get a chance to play with one of these last year? Should I pass these around real quick? Pass it around? All right. So here's what I want you to do when you get it. When this gets to you, here's what I want you to do. Use your pinky. Well, so first of all, only look at the side labeled newtons. Do not look at the side labeled grams. You will go blind. Why?
They're super small. Big numbers. That's units of.
Because that's units of mass. Okay? This spring does not intrinsically measure mass. It measures force. Okay? Mass is a measure of matter. If I took this to outer space and put a 1 kilogram mass on it, would it weigh 1 kilogram? No, because there's no gravity, right? This does not measure mass, it measures force. So dear Ticket, which apparently is the name of the company that made this. You're garbage. Newtons.
It works on Earth.
All right? I know. All right, so anyway, so here's what I want you to do when you get it. Use your pinky. Pull with 1 newton. It's barely any force. All right? Then pull with 20 newtons. You're probably not going to be able to do that or you'll cut your finger, so pull with 20 newtons. Cool. And just get a sense for what 20 newtons feels like. Okay? And be aware of 20 newtons is more force than just 10 newtons. Like, but what I want you to be conscious of is that you have to pull harder to get to 20 newtons, okay? So you're measuring how hard you're pulling. And then similarly, you can push. Good? All right? I know that sounded very basic, but I want to make sure you guys understand that you're measuring how hard you're pushing or pulling. 3, 4, 5, 6. Okay. We just set them on by the hole puncher thing back there. Guys, grab your papers on the way out. Otherwise, they get recycled. All right. Everybody good? Oh, yes.
Very quick. Number 2 on the homework. Is that true or false?
Oh, it's multiple choice.
Oh,
sorry. Yeah, I should have labeled it.
it.
All right, everybody good? Okay. All right. So there are different types of forces that you'll be expected to know about. These will hopefully ring a bell. Force of gravity. All right. Remember, the force of gravity is just the mass times the acceleration of gravity. Last year I used MAG. This year I'm probably going to switch over to MG, and you'll just need to remember it pulls down, so add in that negative sign. Good? All right. Using MG is going to be helpful because remember I keep telling you guys we're going to run into problems with no numbers. A lot of times our answer is going to be written in terms of G. Okay? So it's at this point that we want to make that transition from AG of negative 9.8 to G, which is just 9.8. Clear? All right. Other forces. Clearly, people can push stuff, so we'll talk about the force of Roy. Remember, anytime something is in contact with the surface, there's a normal force. What direction does the normal force always point in without exception? Not necessarily up. Perpendicular to the surface that it's in contact with. Okay? So, right now, the duck is not moving that way. Why not? Because the normal force from the board is pushing the duck that way, right? Okay? If I take the duck and put him on this inclined plane, right now the normal force is pointing up. Now it's pointing at a weird angle, right? Yes. Why do I keep wanting to tell you Kate? I don't know where this is coming from. Sarah.
This is also really optional. Why do you like ducks so much?
I don't. My honors, and my AP students last year brought all these ducks in. They're not even mine. Yeah. Cool.
I remember Kurt told me.
All right, tension. Remember, tension is the force exerted. Tension is the force exerted by a rope or a chain or a cable. All right. For the next few months, the tension at both ends of our rope or cable will always be equal. Okay? When we get to pulleys that are not massless, that will change a little bit, okay? But for now, if you've got a rope that attaches two things and you use the rope to pull, one thing with the other thing, the tension at both ends is equal. Cool? Spring force, I'll use Fs for spring force. Eventually we'll get back to Hooke's law. Honestly, we won't get to it until we get to energy. So for now, we won't run into springs a ton, but just they are there. Force of friction comes up partway through the homework. Remember, there are two types of friction, static and kinetic. Here are things I remember people struggling with. Static friction, it's lazy, right? So that means that if there's 100 newtons of friction, maximum between this table and the floor, then if I push with 10 newtons, friction pushes back with 10, right? If I push with 40, friction pushes back with 40. 90, 90, 100, 100, 101, now it moves, right? Good? All right, once it starts moving, then we're no longer talking about static friction, we're now talking about kinetic. Here's the thing that people kept tangling up last year. What direction does kinetic friction always act without exception?
Opposite the way that you're trying to move it.
Okay.
Direction of motion?
Opposite the direction of motion. Opposite the direction of motion. Okay? So if you've got, I always use the Superman example, right? So if you've got a bus that's sliding along this way, okay, and there's a baby over here, right? And Superman's trying to save the baby. Superman's going to get in front of it. Here's Superman. So here's the force of Superman, right? What direction, point for me, what direction is friction acting in? To the left, because friction is resisting the motion of the bus. Right? If Superman wasn't there, wouldn't friction be trying to stop it? And what's Superman doing? He's sort of helping friction, right? Okay? So the force of friction, the force of kinetic friction doesn't oppose motion. I'm sorry, try that again. The force of kinetic friction doesn't oppose force, it opposes motion. Okay? So in this example, the school bus is sliding that way. Friction doesn't want it to, so friction's going to go the other way, no matter what the other forces on the object are doing. So, let me say one thing, then I'll get your question. Eventually, we're going to get to inclined plane problems. If you've got a block sliding down the ramp, which way is friction going, no matter what? Up the ramp. If you've got a block sliding up a ramp, no matter what, which way is friction going? Down the ramp. No matter what. Follow? Peter?
I'm good now.
You sure?
Yep.
Okay. All right, and then finally, so here's going to be the deal. Drag force. This is the one thing that's new this chapter. All right? So last year we talked briefly about terminal velocity. So we'll talk about that again. What we didn't do is we didn't learn how to... So do you guys remember, why was air resistance difficult to deal with? Anybody remember? Because it changes. What does it depend on?
Shape of the object.
Shape of the object and the surface area, and more importantly, something else.
Density of the air.
Say it again.
It's spinning.
Spinning, yes.
The speed of the object.
There you go. It depends on the speed of the object. But then say it louder, Mr. Getting Mad. All right, it depends on the speed of the object, right? As an object falls, it goes faster and faster, and so there's more and more air resistance, right? And since the force isn't constant and it depends on the velocity, and the force determines the acceleration, which affects the velocity, you get into the spiral of doom that like, I don't know how to solve it, because there's too many things changing at once, right? We're going to learn how to solve those problems. All right, so here's the way I set up the homework. If you flip through the homework, if you look at section 4.2, it's drag. So what I'm going to do is tomorrow or Friday, we're going to do notes on drag. All right, and I'm going to assign one of those problems on each of the other assignments. You know what I mean? So you'll have like one problem one day. You'll have a chance to try it, we'll go over it. You'll struggle with it, we'll go over it, and then you'll have a chance to try the next one the next day. Does that make sense?
Yeah.
Okay? So that drag section, we're just going to do one assignment per day, or one problem per day on it. All right? Questions? All right. Let's see. So what else do we need to know? So remember, forces measure how hard you're pushing the object. Remember, it's possible to push an object without it moving. It's possible to push it one way while it moves another way. Here's a real simple example of that. When I throw this pen up in the air, after I let go of it, what direction is it moving right after I let go of it? Up. What's the only force on it? Gravity, which points down. Okay? So if I give you a drawing that looks like this, don't assume that the object is moving down. It could be going up. Maybe I just threw it and it's moving up. Okay? Don't confuse force with motion. All right? Just like velocity, force can be negative, so we'll always make our force of gravity negative. Remember, we don't need to distinguish between a push or a pull. Okay? What's more important is the direction the object is being pushed or pulled in. Good? Is this all ringing a bell? Any problems with any of it? Is this helpful? A few thumbs up. Good enough? All right. All right, net force, you guys know this. It's the total of all forces. There's a technical thing called the principle of superposition of forces. Basically, it means this. Suppose you've got an object with, I don't know, 10 newtons this way and 2 newtons that way. That is exactly the same. As far as the motion of the object is concerned, that is exactly the same as that. Okay? So, cool? All right. So that is the principle of superposition for forces, I guess. All right, let's see. Free body diagrams. So remember, when you make your free body diagrams, you're going to draw a free body diagram for one object, right? That's why they're called free body diagrams. All right, so you should only have one object in your drawing. Technically speaking, when you make a free body diagram and when you do the AP test, you don't. I always draw a box for the object and I write the mass inside it, just because it helps me kind of keep all my information organized. Technically, you're supposed to just use a dot to represent the object, okay? Which I don't like, but technically that's the way you're supposed to do it. What I've usually seen is on most problems, if it wants a free body diagram, they'll draw the dot for you, and you just have to draw the arrows in, okay? So just know that. I'm going to continue to use boxes, and then at the end of the year when we start doing more practice problems from the AP test, we'll start talking about, we'll switch over to dots. It's no big deal. All right. Let's see. The only forces that you draw are the forces acting on the object. Okay? So if I push this desk, you guys all know that there's a reaction of the desk pushing me, right? If I'm trying to make a free body diagram for the desk, which of those two forces do I draw? Me pushing the desk, right? Because that's the force that acts on the desk. All right? You need a different arrow for every force. All right? Every force gets its own arrow. Don't combine them. Okay? If there are 10 forces acting on your object, there should be 10 arrows coming out of it. Okay? Remember, your arrows always point out of the object. They never point in. If it helps you process, you can draw on your axes. Okay? Remember, when we get to inclined planes, we tilt the axes, right? But that doesn't really change the problem. And then here's one other thing. Technically speaking, and I believe that the AP test is worded such that it tells you this. Technically speaking, when you do a free body diagram, you draw the forces, not the components. Okay, so if you've got a box with a force at a weird angle and it says to make a free body diagram, then draw the force at a weird angle. All right? For problem-solving purposes, though, 1,000 times over, you absolutely want to split that up into components, right? Okay? So I will always make that diagram with the forces and components. And then if it explicitly says make a drawing, you know, a free body diagram of the forces without components, then I'll draw that separate. Make sense? Okay, cool. And then remember, if you want to write down acceleration or velocity or anything, you can do that, but that's sort of not technically a part of the drawing. You sort of draw it off to the side. Cool? Probs? Okay. We'll talk about systems later. All right, so here's, I guess I should comment real quickly. So everything we're learning here is Newton's laws, right? So just recently, the most recent Nobel Prize in science was given because they discovered gravity waves, like proved evidence Gravity waves exist. It's a thing. All right. So using that approach, gravity sort of isn't a force in the true sense of forces. It's a warping of space and time. All right. So anyway, so technically speaking, the stuff that we're learning here is, I don't want to say it's inaccurate because it works on a small scale, right? Okay. So the only time that Newton's laws don't work is if you're talking about things where your object is moving at a very, very high speed, approaching the speed of light, because then you need to worry about relativity. Or if you're looking at things that are very, very small at the atomic scale, okay, then things get complicated. But obviously, everything we're going to be doing is going to be, sort of motion of daily, everyday objects. So Newton's laws still work. Okay? All right. Newton's second law. Remember, the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. Okay? The more mass something has, the less it will accelerate under a given force. Right? Because it has more inertia. It's more resistant to a change in motion. And the more net force you have on an object, the more it will accelerate, right? The harder you push it, the more it will move. Does that hopefully ring a bell? All right. The thing I will remind you at this point, we know two different equations for net force. There's the Newton's second law equation for net force and the definition of net force. What's the definition of net force, you guys? The sum of all the forces. All right? So as you're solving force problems, that's got to be priority number one. Figure out your net force. And there are two ways to do it. If you know all the forces, then add them up. All right? Now, be careful. When you add forces, they're vectors. So if they act at weird angles, you need to do vector addition. Find the components and add the components. Okay? Or, if you know the acceleration, then find the net force. All right? If the problem gives you enough information to find that acceleration, then find the net force. All right? Now, again, because net force is a vector, that means either mass or acceleration must be a vector. Which one's the vector? Acceleration. This equation shows us that the net force and the acceleration are always in the same direction. Okay? The direction of your acceleration vector is always in the same direction as your net force. Clear? All right. Problems? Is anybody like, whoa, I have no idea what you're talking about? Are we all good? I don't know why. For some reason lately I keep wanting to use the word copacetic, and I don't know why. All right, mass is a measure of inertia. You guys all know what mass is, right? Cool. Measure how much matters in an object. There's the second law again. We just talked about that. Let's see. All right, so this one is basically just showing you what I was just talking about, that the acceleration always points in the same direction as your net force. All right, so let's run through this. So for this first example, it says, for example, a 10-kilogram box is being pushed forward across a horizontal surface with a force of 70 newtons. So let's draw that. Here's our box. Here's the always amusing force of U, 70 newtons. Okay, and then the problem tells you that it's accelerating forward. Oh, I forgot to put my mass, 10 kilograms. So it's accelerating forward at 3 meters a second squared. Also forward, right? So, what can I use that information to find? Yeah, eventually I can find the force of friction in 2 steps, but in 1 step, what can I find? Net force. All right, this is like rule number 1. If you know the acceleration, find the net force, okay? So our net force here is going to be mass times acceleration. Our net force is going to end up being 30 newtons, right? Make sense? Any probs? Okay. And so that means that I have to have a force of friction because that's the only way my net force could possibly be 30, right? So which way is my friction going? To the left, it's got to be. We know that it's kinetic, so I guess I can go ahead and tack that K on there. It's got to be what? Negative 40 newtons, right? And now I know what direction the box is moving, don't I? Point for me. What direction does the box have to be moving? That way. How do I know? Because friction's going the other way. Remember, friction opposes the motion. So draw in your velocity vector if you want, and just label it with a V. Can I find the velocity? Can we find the velocity, you guys? Exactly. No. We don't know the starting velocity, and I haven't given you a time. The velocity is always changing. So the question didn't even make sense, right? Okay, Maggie, what's up?
Oh, I said no as a joke, and then I was right.
Oh. Do you understand why we can't?
Yeah.
You sure?
Yeah, I understand.
Okay. Everybody good? Okay. Now, in the next example, it says a box is being pushed forward across a horizontal surface with a force of 70 newtons, and it's accelerating backward at 3 meters a second squared. So let's draw this. So here we go. It's being pushed forward. So here's the force of U, 70 newtons. But now our acceleration is negative 3 meters a second squared, right? So what does it mean for it to be accelerating backwards? Does that mean it's moving backwards? No, it just means that the acceleration is in the opposite direction of the velocity, i.e. our velocity is decreasing, right? Okay? So now my net force is negative 30 newtons. And therefore, what does my force of friction have to be? Negative 100 newtons, right? Follow? And again, my velocity's got to be this way, right? Because friction's going the other way. All right. Problems, you guys? Am I going too quick? Are we? Is this all good? This is like Newton's laws in 22 minutes, apparently. Ooh. Hey guys, I gotta go. All right. Examples, no. Oh, here's the thing we didn't talk about last year. All right, so I kind of talked the other day about inertial frames of reference. Do you guys remember how we defined it?
If two of the three objects are not accelerating, right?
Okay, yeah, so it has to do with acceleration, sure. But we need to be focused on one frame of reference. Oh my gosh, are we all looking out the window? What's going on? Do we see smoke?
Are we gonna get out?
I think we're okay.
Yeah. We'd have it siren.
Okay. All right, so Daniel's right in that it sort of deals with acceleration, all right? So very frequently, the way that an inertial frame of reference is defined is, I can't say this. In the notes last time, we did an example where there was a bus and a cheetah or something. No. Did we do a cheetah example?
Yeah, pickup truck.
Pickup truck and a cheetah, and they were going in opposite directions or something?
Yeah.
Is that a thing? Okay. So anyway, the point was the pickup truck was moving at a constant velocity, and so both the person on the ground and the person in the pickup truck measured the same acceleration for the cheetah. Does that ring a bell?
Yeah.
It was something like that. All right. So the reason that that worked was because both the pickup truck and the person on the ground had no acceleration. So both the ground and the pickup truck are inertial frames of reference because neither one's accelerating, right? But that sort of doesn't make sense because when you say that the person isn't accelerating or the pickup truck isn't accelerating, not accelerating with reference to what? To answer that, you got to pick some other frame of reference which may or may not be accelerating, right? So the technical definition of an inertial frame of reference is, an inertial frame of reference is one for which Newton's laws are true. Okay? So if you're in an elevator and you drop a ball, but it doesn't fall, oh, it must not be following, we must not be in an inertial frame of reference. What's the elevator got to be doing? Accelerating which way? Downward. How fast? 9.8 meters a second squared, right? You've got to be falling, right? Okay, but that would be a non-inertial frame of reference because I just released a ball, but for some reason it didn't obey Newton's laws, right?
That's weird.
Okay. Here's another weird example. Imagine that you had, so here's the Earth. Here's the North Pole. Okay, here's a long frictionless ice thing. Okay? And you take a hockey puck and you slide the hockey puck. Okay? So we've learned that on frictionless ice, if you slide a hockey puck, it'll keep going in a straight line, right? Okay? So if I do this on my ice rink on the Earth, what's the hockey puck going to do? Keep in mind the Earth is rotating, right? So the hockey puck is going to go in a straight line, but underneath it the Earth is going to rotate, right? Do you see what I'm saying? So relative to you, the hockey puck is actually going to veer a little bit off to the side, isn't it? As the Earth sort of turns underneath it. So if you're standing here watching it, there's you scratching your head. What? Let me finish my train of thought and then I'll get you on it. So if you're standing here watching it, for some reason the hockey puck is turning, right? Is there a force that's making it turn?
Yeah, people rolling aside because you're curling out.
Stop. That's good. All right, so assuming that nobody's curling here, is there a force making the hockey puck turn? No.
There's not turning.
It's right. So technically speaking, relative to some stationary point in the universe, it's going in a straight line, and the Earth is turning underneath it, right? Here, do this. Let's pretend it's not the Earth. Look, it's a merry-go-round. Same thing. All right? So if I sit at the center of a merry-go-round and I slide a thing towards the side, as the merry-go-round turns, it's going to kind of go in a straight line, but if you're sitting on the... shoot. That's more confusing. But do you guys see what I'm saying? That the fact that your frame of reference is rotating is going to sort of change the way that you perceive the motion of the object. Follow? All right, and so seemingly from your perspective, it's going to seem to turn with no force on it, so that's a non-inertial frame of reference. Good? All right, if you don't get that, I've never seen a question about inertial frames of reference on the test, even though it's technically in the curriculum. Cool? All right, questions on it? Oh, yeah, Evan, I'm sorry.
I don't know if you answered that while I was over there, but if you're on the Earth too, or like, if you're...
What do you got?
I don't know. Like if you're on the Earth, isn't it like not curving for you too, because you're on the same place?
No, that's what I'm saying. So in the original example, the rink was frictionless, right? So here, let me do this. Don't ask why you've only got one arm. You're the drummer from Def Leppard. Anybody?
Def Leppard.
Oh, shoot, I didn't want to do that. Okay, so check it out. So let's pretend that the Earth isn't rotating. Okay? The Earth is just stationary. And you slide a hockey puck. So here's your hockey puck. It's going to go in a straight line, right? Okay? But the fact that the Earth is rotating is going to affect... Why is... Oh, because I haven't covered up both things.
Still haven't covered up the black one.
God bless it.
Blue smart marker?
No, that's crazy talk using the... Okay, so as the Earth turns, right? Right? So the hockey puck isn't actually going to go in a straight line. It's going to turn to the side, right? Does that make sense? So that the path the hockey puck follows is not going to be the red line. It's going to be this green line relative to you. So now the hockey puck just turned with no perceivable force on it. It has not followed Newton's laws. That's why I had to make this a super long thing. You're right. The Earth doesn't turn that fast, so in most examples it doesn't matter. But if you had, that was why I said you have a super, super long ring.
You're like giant.
Good? So yeah, this only works if the rink goes super long. And all right, did that answer your question then, Maggie?
No, my question was more dumb than that. It was just
I almost said I doubt it, and that would have been... What do you got?
This is the reason why you can't walk in a straight line.
Say that again, why you can't walk in a straight
You
line.
can't walk in a straight line blind.
Oh, is that true? I didn't know that. I don't know why that is. Oh. All right. I'm already talking longer than I meant to. All right, so Newton's first law. Why do I have the first law after the second law? Honestly, it was a mistake, but tell me why. Why would it make sense? Doesn't? What does Newton's first law tell us? Object at rest stays at rest. Object in motion stays in motion. Unless, yes. But remember last year I told you guys like the consolidated version of it?
No. I don't remember hearing you say it.
If the net force is 0, then your acceleration is 0, and your velocity is constant. Doesn't the second law tell us that? Right? If acceleration is net force over mass, then if your net force is 0, your acceleration is 0. So once you know the second law, you don't even need the first law, right? Take that, first law. Does that make sense? All right, so remember, these three statements are equivalent. If the net force is 0, then automatically your acceleration is 0 and your velocity is constant. Does that mean it's not moving? No, it means that if it's moving at a constant velocity. So, there it is. There's my version of the first law. I can't believe I did second law before first law. That's really weird. All right, so remember, if you want to change the velocity, you have to have a net force. I think everything else there we talked about. All right, cool. That was that. All right, so tomorrow we're going to do driving force. Tomorrow would be, if you are, like, is there anything going on tomorrow? Is there any reason why people are going to be out tomorrow? What's that? Friday. I don't care about Friday. All right, I want to make sure everybody's here for the driving. Okay, cool. All right, I'm going to shut up. You guys have, what, 15 minutes? 10 minutes, I mean? Okay, get started on the 4-1 assignment.